Lecture 4. Chemical Foundations, Elements, Atoms, and Ions. Objectives. Learn about the relative abundance of the elements. Learn the names of some elements. Learn the symbols of some elements. Learn about Dalton's theory of atoms. Understand and illustrate the law of constant composition. Learn how a formula describes a compound's composition. Learn about the internal parts of an atom. Understand Rutherford's experiment to characterize the atom structure. Understand some important features of subatomic particles. Learn about the terms isotope, atomic number, and mass number. Understand the use of the symbol XAZ to describe a given atom. Learn about various features of the periodic table. Learn some of the properties of metals, nonmetals, and metalloids. Learn the natures of the common elements. Understand the formation of ions from the parent atoms and learn to name them. Learn how the periodic table can help predict which ion a given element forms. Learn how ions combine to form neutral compounds. 1. Relative abundance of the elements. Although more than 100 elements are known, only a few dominate the composition of matter around us. In the universe, hydrogen and helium are the most abundant. In Earth's crust, oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium dominate. In living organisms, oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus are the most important. Key idea: chemistry focuses less on how many elements exist and more on how a few key elements combine to form all substances. 2. Names and symbols of elements. Each element has a name, often from Latin or Greek. A symbol of one or two letters, first letter capitalized. Examples: hydrogen H, carbon C, sodium Na from natrium, iron Fe from ferrum. Why symbols matter? Chemical language is universal. Scientists worldwide understand formulas and equations written with symbols. 3. Dalton's atomic theory. John Dalton, early 1800s, proposed the first modern atomic theory. Matter is made of tiny particles called atoms. Atoms of the same element are identical. Atoms of different elements differ. Compounds form when atoms combine in fixed ratios. Chemical reactions rearrange atoms. Atoms are not created or destroyed. Importance: Dalton explained why substances have fixed compositions. 4. Law of constant composition. Also called the law of definite proportions. A given compound always contains the same elements in the same mass ratio. Example: water is always H2O. 2 hydrogen atoms for every 1 oxygen atom. This ratio remains constant regardless of the water source. Connection to formulas. Chemical formulas are direct expressions of this law. 5. The chemical formulas in composition. A chemical formula tells which elements are present, how many atoms of each element are present. Examples: CO2 1 carbon, 2 oxygen atoms. NaCl 1 sodium, 1 chlorine. Subscripts are ratios, not actual counts in a sample. 6. Internal structure of the atom. Atoms are not solid spheres, they contain subatomic particles. Particle. Charge. Location. Relative mass. Proton. +1. Nucleus. 1 AMU. Neutron. 0. Nucleus. 1 AMU. Electron. -1. Outside nucleus. 0 AMU. Key idea: almost all mass is in the nucleus, most volume is empty space. 7. Rutherford's gold foil experiment. Ernest Rutherford bombarded thin gold foil with alpha particles. Observations: most particles passed straight through. A few were deflected. Very few bounced back. Conclusions. The atom is mostly empty space. A small, dense, positively charged nucleus exists. Electrons occupy the surrounding space. This experiment overturned the plum pudding model. The plum pudding model. Proposed by J.J. Thomson after discovering the electron, 1897. Idea: the atom was a positively charged pudding with negatively charged electrons, the plums, embedded throughout. Prediction: if you shot particles through matter, they should pass straight through with only tiny deflections, because the charge was spread out evenly. Classroom trick question. True or false, in Rutherford's experiment, most alpha particles bounced back, proving that atoms are solid. Answer: false. Why? Only a few bounced back, most passed through, showing atoms are mostly empty space with a dense nucleus. 8. Atomic number, mass number, and isotopes. Atomic number, Z number of protons, defines the element. Mass number, A protons plus neutrons. Isotopes, atoms of the same element with different numbers of neutrons. Example: carbon-12 and carbon-14 are isotopes of carbon. 9.
Atomic symbol notation, vacío, subíndice mayúscula Z a la mayúscula
Okay, the atomic symbol notation is this one where X represents the symbol of the element, Z is the atomic number or the number of protons, and A is the mass number, that is the protons plus the neutrons in the atom. For example, in sodium, the atomic number is 11. It means that it has 11 protons. And 23 is the atomic mass. If you subtract 23 minus 11, you will get the number of neutrons. Here is incorrect, neutrons. Neutrons. Okay? Then the number of neutrons is determined by subtracting the atomic mass minus the atomic number. Let's continue then. Let's see what is the periodic table.
The periodic table. The periodic table organizes elements by increasing atomic number, similar chemical properties in columns, groups, key features, groups, columns, similar valence electrons, periods, rows, energy levels, metals on the left, non-metals on the right, metalloids in between.
Okay, let me stop into here. Look, this is the periodic table. You can see that you have columns. The columns are the groups. You have periods. The periods are the rows. And you can see that here we have the green elements are non-metals. The pink ones are the metalloids that have characteristic of non-metals and metals, and that the metals are the gray or violet ones. These are the metal ones. So let's see which one are the characteristic of metal, non-metals, and metalloids.
Metals, non-metals, and metalloids.
Okay, what about the metals? Let's see which one are the characteristic of metals.
Metals, shiny, conductive, malleable, form cations, Na, Fe, L. Non-metals, dull, poor conductors, form anions, O, N, Cl. Metalloids, intermediate properties, C, B. 12. Common elements and their nature. Sodium Na, reactive metal, forms +1 ions. Chlorine Cl, reactive nonmetal, forms -1 ions. Calcium C8, essential for bones, forms +2 ions. Oxygen O, vital for respiration, forms -2 ions. 13. Formation and naming of ions. Atoms form ions by gaining or losing electrons. Cations plus lose electrons, metals. Anions gain electrons, nonmetals. Examples:
Nada mais é.
Cl plus Ec.
Look, sodium loses one electron and get a positive charge. Chlorine gains one electrons and made the chloride ion. Let's see how we can name the cations and the anions.
Naming. Cations keep the element name, sodium ion. Anions end in alide, chloride ion. 14. Predicting ions using the periodic table. Group 1 plus 1 ions. Group 2 plus 2 ions. Group 17 minus 1 ions. Group 16 minus 2 ions. The periodic table is a predictive tool, not just a chart. Why the periodic table is predictive. Atomic structure patterns. The arrangement by atomic number reveals repeating trends in electron configurations. From this, we can predict reactivity, ion formation, and bonding behavior. Periodic trends. Properties such as atomic radius, ionization energy, electronegativity, and metallic character vary systematically across the periodic table. Example, moving down group 1, alkali metals, reactivity increases because outer electrons are farther from the nucleus. Ion formation. The table predicts which ion elements will form. Group 1 plus 1 cations. Group 2 plus 2 cations. Group 17 minus 1 anions. Transition metals variable charges. Compound prediction. By combining charges, we can predict formulas of neutral compounds. Example, magnesium Mg superscript 2 and chlorine Cl MgCl2. Discovery of new elements. Historically, Mendeleev left gaps in his table and correctly predicted the properties of elements yet to be discovered, such as gallium and germanium. That's predictive power in action.
Okay, let me stop into here. Look, you can see here, this is what we call the S block. The S block is made of group 1, that has a specific name, the alkali metals, and group 2, that is made of the alkaline earth metals. Group 3 to 12 belongs to the transition metals that are in the T block. Group 13, 14, 15, 16, 17, and 18 are what we call the SP block. And they are the boron group, the carbon group, the nitrogen group, the oxygen group, and the halogens group. The last group is the noble gases because they are inert. They don't react almost. And down you can see the F block. The F block is made of the lanthanides and the actinides. Let's go to some questions. Tricky question, of course, as you will have in this class.
Classroom trick question. True or false, the periodic table only organizes known elements. It cannot predict properties of undiscovered ones. Answer, false. Why? Mendeleev's table predicted properties of elements before they were discovered, and modern periodic trends still allow us to anticipate the behavior of new or synthetic elements. So when you look at the periodic table, you're not just seeing a chart, you're holding a map of chemical possibility. 15. Formation of neutral compounds. Ions join together so that their overall charge becomes neutral. Examples.
Here you have the sodium cation plus chloride anion make sodium chloride. That is a compound. And if the sodium is positive and the anion is negative, sodium chloride is neutral, no? calcium 2 plus and two anions of chloride make calcium chloride. Key role, nature favors electrically neutrality.
Summary. This lecture establishes the foundation of chemistry. Elements and atoms explain the composition of matter. Atomic structure explains chemical behavior. The periodic table allows prediction. Ions and charges explain how compounds form. These ideas will support stoichiometry, bonding, reactions, and chemical calculations in all future chapters. Interesting notes. 1. Lithium La, a small element with a huge impact. Basic facts. Symbol, Li. Atomic number, 3. Group 1, alkali metals. Charge formed, Li. Why is lithium special? It is the lightest metal. Extremely reactive, especially with water. It has a very high charge-to-mass ratio, making it chemically powerful. Key applications. Battery lithium-ion batteries, phones, laptops, electric vehicles. Brain medicine, lithium salts used in bipolar disorder. Small airplane aerospace, lightweight alloys. Fire nuclear and fusion research. Chemical behavior. Loses one electron easily forms Li. Similar chemistry to Na and K, but stronger interactions due to its small size.
So let me stop into here. Look, what are the applications of lithium? Well, it can be used in nuclear and fusion research. It can use as lightweight alloys. Also, it can be used in medicine because lithium salts are used in bipolar disorder. And also, lithium is in all the batteries that we have in our phones, laptops, electric vehicles. That's why nowadays the world is looking for lithium because we, in our devices, the devices that we have around us, all of them contain the batteries of lithium. So, what is the chemical behavior? Lithium loses one electron easily to form the cation, lithium cation. Similar chemistry is the one for sodium and for potassium, but a stronger interaction due to its small size. What is the small size? Lithium is very small in comparison with sodium and with potassium. What are the rare earth elements? Let's see. Let's go.
2. What are the rare earth elements, REs? Despite the name, rare earth elements are not truly rare, but they are. Dispersed in low concentrations. Difficult to separate chemically. They include lanthanides, Lu, plus scandium, Sc, and yttrium, Y. Round pushpin located in the F block of the periodic table. 3. Why rare earth elements are so important. Rare earth elements have unique electronic structures, partially filled F orbitals, which give them exceptional properties. Strong magnetic behavior. Sharp optical emissions. High catalytic efficiency. Other elements do not easily replace these properties. 4. The key rare earth elements you should know. Neodymium, Nd. Used in powerful permanent magnets. Essential for wind turbines, electric vehicle motors, headphones and speakers. Neodymium magnets are among the strongest magnets known. Lanthanum, La, Used in camera and telescope lenses, petroleum refining catalysts, improves optical clarity of glass. Cerium, Ce. Used in catalytic converters, self-cleaning ovens, glass polishing. Cerium can easily switch oxidation states, making it an excellent catalyst. Europium, EU. Responsible for red colors in TV screens, LED displays. Critical for modern display technology. Yttrium, Y. Used in medical lasers, cancer treatment, superconductors. 5. Chemical characteristics of rare earth elements. Common features. Usually form +3 ions. Chemically very similar to one another. Hard to separate due to similar ionic sizes. Example.
Here you have how this element, neodymium, form the 3+ cation, losing 3 electrons. Which one are analytical challenge? The analytical challenge, well, they are similar, and they make what we call the rare earth chemistry, one of the most demanding areas of separation science. Here you have some, for example, lithium is in the S block. The typical ion is positive +1. And important is that it is used as energy store in the batteries. The reactivity is very high and the strategic value is very high too. The rare earth elements are in the F block. As I showed you before, the typical ion is +3, and the characteristic that they have are magnetism, optics, electronics. The reactivity is moderate, but the strategic value is very high. You can see how the United States of America is looking for this kind of elements everywhere in order to improve even the new devices and the artificial intelligence. Let's continue with lithium.
Lithium and rare earths are critical elements for green energy transition, electric vehicles, defense technologies, advanced electronics. Control over these elements has become a geopolitical issue, not just a chemical one. 8. Big picture for students. Lithium shows how simple atomic structure can lead to powerful applications. Rare earth elements show how subtle electronic differences control advanced technology. Together, they demonstrate why chemistry is central to modern civilization. One sentence takeaway. From the tiny lithium atom powering your phone to rare earth elements driving global technology, the periodic table is not just a chart, it is a map of modern life.
Okay, I want you to pay close attention to this because it's what I wanted you to understand in this lecture. Remember that from the tiny lithium atom powering your phone to rare earth elements driving global technology, the periodic table is not just a chart, it's a map of modern life. So look at this. I'm going to go again to the periodic table, and you can see the groups, their names, the D block and the F block, the position of all the elements in the periodic table. And remember that this order is from the a small atomic number that is a hydrogen, Z equal 1, to the heavier elements that are here at the bottom and right part of the periodic table. Well, that's all in this lecture. Please remember how the atoms are made of electrons that are in a cloud around the nucleus. The nucleus is a small part of the atom, but most of the atom is empty space where we can find in orbitals the electrons. We are going to study deeper this the structure of the atom in other chapters. That's all for now, and remember how to calculate the number of protons, the number of neutrons, and the number of electrons. See you in the next lecture.